This is 1.4 sigma notation. Recall that a sequence is defined as A sub n, where n is the term number and A sub n is the term value. We've been working with arithmetic and geometric patterns. Arithmetic had a common difference and geometric sequences had a common ratio. You've been exposed to other patterns as well, and we're going to venture into these soon enough. When you take the terms of a sequence and add them together, the sum is referred to as a series, and we can use something called sigma notation. So this is the sigma right here, okay, to the right side. You have the index is a letter, usually K or I or J. And then you have the lower limit of the summation and the upper limit. And then A sub K is going to be that explicit rule for the sequence. So we learned an A sub n formula and a G sub n, the explicit. So again, a series is the sum of the terms of a sequence. The symbol sigma is a Greek letter S, and it represents the sum of the terms. Shown below are the specifics about sigma and summation notation. So what we're going to do now, and we'll do each one of these. So we would read this as the summation k equals 1 to 5 of 2k. Notice the parentheses matter. What you're going to do is you're going to do iterations here of plugging in k is 1, then you add, k is 2, then you add, k, plugging in k is 3, plugging in k is 4, and k is 5. I write so large, let me shrink this so I can do the other work. Okay, so then you can easily do this by hand. That's 2 plus 4 plus 6 plus 8 plus 10. And that gets you 30. All right, letter B. Let's try this one. So I'm going to go through. Notice again the parentheses around the n squared minus 1. And look at part C, because we will actually do this one differently. Also, notice the index. They don't always start at 1, even though oftentimes they do. So this says I have the summation. N is going to run from 8 to 10. That means I'm going to plug in n is 8, then n is 9, and then n is 10. So this is going to be 8 squared minus 1 plus 9 squared minus 1 plus 10 squared minus 1. So that's 63 plus 80 plus 99. When you add these up, you should get 242. All right, so in letter C, I want you to notice I don't have a parenthesis around the n squared, so it really matters. So this is going to be 8 squared plus 9 squared plus 10 squared, and then we are literally just going to subtract 1. So what I want you to notice, these are not the same. So parentheses matter, okay? The parentheses matter. Moving on, oops, this is a little typo. This should be 162. So fix that on your paper. It says, write the following series in sigma notation. Okay, well, what you need to do is you need to see if you can figure out the explicit formula. Okay, you want to first determine the explicit formula. So does it appear that I'm adding the same amount? No. Then let's see if it's geometric. And what you do is you're going to take the g sub 2 divided by the g sub 1. So that's negative 108 over 162. And I get negative 2/3. Let's just make sure that this is true. So then this one is geometric. Then we're going to use G sub n equals G sub 1 times r to the n minus 1. So my G sub n is 162 times negative 2/3 to the n minus 1. All right, so how many terms are there? There's 1, 2, 3, 4. So you can pick whatever letter you like. Oftentimes I either do a K or an I. So I'm going to say K runs from 1 to 4, and then all you do is put, now be careful, we're going to use a K instead of the N. So it's 162 times, in parentheses, negative 2/3 to the K minus 1. So it really is that simple. Sigma notation is just find your explicit formula. Typically, it will be arithmetic or geometric. You have to determine that and then do the summation. So sometimes you have to figure out how many terms you have. So that can be an issue. But we learned how to do that in an earlier section. All right, now let's revisit the binomial expansion theorem. If you recall, x to the 5th plus 5x to the 4th plus 10x cubed plus 10x squared plus 5x plus 1. Remember that was 1, 5, 10, 10, 5, 1 is the same thing as x plus 1 to the 5th. So we can actually rewrite this using sigma notation. So if I do that, and if you don't like the n choose r here, we can use this notation. I want you to notice, so a plus b to the n power. Remember, this was our coefficients. And remember, it always started with 0, n choose 0. And then that's going to be a to the n minus r times b to the r. So let's take a look at letter A. I have the sum. P runs from 0 to 20. So I want you to notice up here, that's n. So my n is 20. The A is here, and there's your B. So this is going to be 4x minus 5 to the 20th. It's really that simple. Now in letter B, of course, so I know my n is 100, but I don't seem to have an A value. Well, my A value is going to be 1, and the B is to the 1. So this is going to be r, and 100 minus r. But thank goodness, 1 to any power is still 1. So this is going to be 1 plus 1 to the 100th, or 2 to the 100th. So isn't this essentially asking us for the 100th row of Pascal's triangle? All right. Then example D, completely factor using binomial expansion theorem. So I want you to remember that, okay, so I'm not quite sure what's happening here with this first term, but if I go to 81, isn't that 3 to the 4th? So maybe I'm getting something to the 4th power. Well, what to the 4th power is 16x to the 8th? That's 2x squared. Now, whoops, okay, so I just caught something here. I'm noticing that the signs are alternating, which means then that's going to be a negative. So that'll be a minus. And I also wanted you to notice, so let's do Pascal's triangle real quickly here, just several rows. So if this was row 0 and row 1, row 2, row 3, row 4, if you look at the number of terms here, do you notice there was 1, 2, 3, 4, and 5? So if the row number is n, the number of terms is n plus 1. So let's just confirm. I had 1, 2, 3, 4, 5 terms. then that has to be the fourth row. So that kind of confirms what we thought. All right, that finishes the notes for us.